Hey everyone, welcome back for another deep dive. Today we're going to be talking about cooling systems in die casting. You've got this molten metal, it's super heated glowing, and you need to cool it down rapidly and precisely to create a solid object. And that's where die casting cooling systems really take center stage.
Yeah, they're critical.
So the source material we're looking at for this deep dive comes from a Chinese manufacturer specializing in aluminum die casting, and they've provided some really interesting insights into cooling rates, factors that influence cooling, specialized cooling devices, and why they believe jet cooling is like the best method.
It's fascinating stuff.
So let's jump right in. One of the first things they talk about is the difference between cooling rate and cooling time. Can you break those down for us? Because honestly, I always kind of thought they were the same thing.
Yeah, a lot of people do. It's a common misconception. You can think of it this way. Cooling rate is like a speedometer. It measures how fast the molten metal solidifies. We're talking seconds here. The quicker the better in many cases. But cooling time, that's more like a stopwatch. It's capturing the total time it takes from injecting that molten metal to ejecting the finished solid part.
So the speed of the cool down versus the total duration.
Exactly.
Okay.
And getting that cooling rate right is really crucial. Too slow, and you risk defects like porosities, those tiny air bubbles trapped in the metal.
Right.
But if it's too fast, you could end up with warping or uneven shrinkage.
So it's a delicate dance. You've got to find that sweet spot.
Precisely.
Now, they also go into the factors that can impact a die casting mold's cooling system. What were some of the things that stood out to you there?
Well, so source highlights a bunch of factors, but for me, the most fascinating ones are the thermal conductivity of the materials involved and the complexity of the part's shape.
Okay, so different materials conduct heat differently, obviously, but how does the shape of the part come into play?
Well, imagine trying to cool down a waffle iron versus a flat baking sheet. That waffle pattern with all those nooks and crannies, it's going to trap heat and cool down unevenly compared to the smooth surface of the baking sheet.
Right.
Same principle in die casting. Intricate shapes with tight spaces and thin walls, they can pose a real challenge for cooling systems.
So it's like trying to evenly cool a plate of spaghetti versus a plain pancake.
Exactly. That's a great analogy.
And speaking of challenges, they also mention these specialized cooling devices. Baffles, thermal pins, and bubblers. What are those?
You can think of these devices as the special forces of the cooling world. They come in for those really tough missions when the standard cooling channels just won't cut it.
Okay, I like where this is going. Tell me more about these cooling specialists.
All right, so a baffle, imagine it's like a strategically placed roadblock in the mold. It forces the coolant to take a detour, increasing the cooling surface area and making sure those tight spots get the attention they need.
Interesting.
Now, a thermal pin, on the other hand, is like a tiny heat sponge. It absorbs a huge amount of heat through a phase change. Think like ice melting to water. And then it releases that heat back to the coolant. They're often used to target specific hot spots.
So strategically redirecting the coolant and absorbing excess heat in critical areas.
You got it.
Now, what about bubblers? What are those?
Picture a miniature shower head.
Yeah.
Spraying coolant directly onto a specific area of the mold cavity.
Yeah.
That's essentially what a bubbler does.
Yeah.
Pinpoint cooling accuracy.
So there's a lot of thought that goes into these cooling systems. You need to understand the material, the shape of the part, and then how to use these special devices to make sure everything cools down properly.
Absolutely. It's a complex engineering challenge.
It sounds like it. All right, so we've covered a lot of ground here. Let's take a quick break and we'll come back and dive even deeper into these die casting cooling systems.
That's good.
So before the break, we were talking about those specialized cooling devices. Baffles, thermal pins, bubblers. They're pretty cool, huh?
Oh, yeah. They're really ingenious pieces of engineering.
Right.
And where you place them in the mold is super important. It's critical to get that optimal cooling.
So let's say we're designing a cooling system for a really complex part, something with lots of thin walls and intricate details. What's the thought process like there?
Well, it's almost like a game of thermal chess. You have to anticipate where the heat is going to build up and then plan your cooling strategy accordingly.
Okay.
Like with those thin wall sections you were talking about. Thermal pins would be your go-to. You'd place them strategically to act as little heat sinks, pulling that excess heat away and preventing any warping or distortion.
And I guess for those tight spaces, those awkward corners, that's where the baffles would come in.
Exactly. You'd use those baffles to redirect the coolant flow, making sure that even those hard-to-reach areas are getting cooled properly. It's all about creating a balanced and efficient flow throughout the entire mold.
This makes a lot of sense. But our source material seems to be really pushing jet cooling as the optimal method. Can you break down what jet cooling is and why they might be so enthusiastic about it?
Sure. Jet cooling is all about speed and precision. It's a two-step process. First, you've got high-pressure water jets that blast the mold, really rapidly extracting heat.
Okay.
Then compressed air is injected to get rid of any residual water, leaving the part nice and dry and ready for ejection.
So it's like a supercharged cooling system,
Mhm.
combining the cooling power of water with the drying efficiency of air.
Yeah, you could say that.
I can see why manufacturers would like that.
Right. From a production standpoint, jet cooling has some really appealing advantages, like it can dramatically reduce cycle times, you can churn out parts much faster, and that rapid cooling also tends to improve part quality. You get fewer of those porosities and shrinkage issues.
Okay, so faster production, fewer defects, happier customers. Sound like a win-win. Are there any downsides to jet cooling, though?
That's a great question. And to be honest, the source material doesn't really mention any drawbacks,
Hmm.
but if we're being objective, there are a few things to think about. Well, first off, those jet cooling systems. They require a pretty big upfront investment. You need high-pressure pumps, air
Wow.
compressors, more complex plumbing, and then there's the energy it takes to run all that equipment.
Yeah, I guess that makes sense.
So there's the cost factor, right?
Right.
Both the initial investment and the ongoing operating expenses.
Right.
And then there's the issue of water usage. Jet cooling can be pretty water-intensive, which might be a concern in areas where water is scarce.
Interesting points. It sounds like jet cooling, while it does have some clear advantages, also comes with some trade-offs. It's not a one-size-fits-all solution, is it?
No,
Uh,
not at all. The best cooling system for you? It depends on a whole bunch of factors. The metal you're casting, the complexity of the part, your production goals, your budget.
So finding the right balance between performance, cost, and sustainability.
Exactly.
Well, this has been really interesting, but I'm curious, what are some of the emerging trends or innovations in die casting cooling technology? What's on the horizon?
Oh, that's where it gets exciting. We're starting to see a push toward more intelligent and adaptive cooling systems.
Okay.
Imagine sensors embedded in the mold,
Mm-hmm.
constantly monitoring temperatures and adjusting the coolant flow in real time to optimize the cooling process.
Wow, so like a mini computer inside the mold,
Yeah, kind of.
making sure everything is cooling perfectly.
Exactly. And we're also seeing a lot of interest in sustainability, like closed-loop systems that recycle coolant to minimize water waste, or even exploring alternative coolants that have a lower environmental impact.
So it's not just about efficiency and performance anymore. It's about making it sustainable, too.
Absolutely. The future of die casting cooling is all about smarter, more sustainable, more adaptable systems.
This is really fascinating stuff, but we've covered so much ground today. I think it's time to let our listeners digest all this information. We've gone from the basic definitions of cooling rates and cooling times, all the way to these really advanced technologies like jet cooling and sensor-driven systems. And we've even touched on the importance of coolant selection and sustainability. So if you're interested in learning more, we've got some additional resources in the show notes, and as always, keep those minds curious, and remember, there's always more to learn.
Yeah, it really is amazing. All this innovation happening with die casting cooling. Who would have thought we'd be talking about? Intelligent molds with sensors that can adjust the cooling in real time.
Right. It's incredible. And it really shows how much effort goes into making die casting more efficient and precise.
Absolutely. But you know what we haven't talked about yet? The coolant itself.
Well, that's true. We got so caught up in the technology, we almost forgot about the liquid that's actually doing the cooling.
Exactly. Our source did mention that. Choosing the right coolant is critical.
Yeah.
So what are some of the things to consider there? Well, the first thing you have to think about is thermal conductivity. You know how well the coolant can transfer heat.
Right.
Water is often the go-to choice. It's cheap, it's readily available, and it's got great heat transfer properties.
Makes sense.
But sometimes you need something a bit more powerful.
More powerful. Like what?
Certain oils,
Yeah.
for example, they can have even higher thermal conductivity than water, so they can handle those really high temperatures and provide faster cooling rates.
Interesting. So it's about matching the coolant to the specific needs of the process.
Exactly.
Okay.
And it's not just about heat transfer either. You also have to think about the coolant's viscosity, its freezing point, and whether it's corrosive.
Corrosive. Why does that matter?
Well, some coolants can be pretty aggressive, especially when you're working with certain metal alloys. Over time, they can actually start to eat away at the mold, which can damage the mold and affect the quality of the parts.
Oh, wow. So you're looking for a coolant that cools effectively, but that's also compatible with the mold material and the whole process.
Right? It's all about finding that balance.
It seems like everything in die casting comes down to finding the right balance.
You got it. Die casting is all about precision and control. Every single variable matters. The temperature of the metal, the pressure of the injection system, the type of coolant. Everything plays a role in determining the quality and consistency of the final product.
Well, this has been a really fascinating deep dive. We've learned so much about cooling systems, from the basics of cooling rates and cooling times to those specialized cooling devices, and even a glimpse into the future with those intelligent cooling systems. I feel like we've barely scratched the surface, though.
Oh yeah, there's always more to explore.
But for our listeners who want to keep learning, we've included some additional resources in the show notes, so be sure to check those out. And as always, keep those minds curious, because there's always more to learn. Thanks for joining us for another deep dive. We'll see you next time.